Okay. Good afternoon. It is February 10th. And today we're talking about inverse trig functions. So, inverse trig functions undo our trig functions. It's just the reverse. So, for instance, if I were to say the sine ratio at the pi over 6 angle, what is the sine ratio at the pi over 6 angle?
Wait, what is that pi? What is the sine ratio of pi over 6? Oh, well,
That would be radical 3 over 2.
no, is it 1 half?
1 half.
Oh,
Oh. All right. So this is the trig that we have been doing. The sine ratio at some angle, the sine value at some angle has a ratio of 1 half. And so this is how we've been doing things. Well, today we're talking about inverse functions. And so we would say, basically, these things get swapped. So inverses, I don't know if you remember when we were talking about inverses, but we swap the x and y, and those are inverses. They swap. And so we would say the sine inverse of some ratio. So if the sine has a ratio of 1 half, then we want to know what is that angle measure, which would be, in this case, pi over 6. So this little to the negative 1 means inverse. It's not exponent, it means inverse. And so you can see how the ratio has changed places with the angle. But the problem is that that's not the only place that sine has, that's not the only angle where we have a ratio of 1 half for sine. So over here, we also have a ratio of 1 half for sine. And so then the question becomes, well, how do we know which answer? Why isn't 5 pi over 6 the answer? Okay, so that's what we want to understand today. So this is pretty straightforward, I think. But we need to understand why there's only one option here instead of 2. That's a problem. It's not a function then. So we have some other notation. Not only can we use this sine to the negative 1 inverse, but we have another word called arc. Sine of 1 half equals pi over 6. Arc sine is the older notation for the inverse function, and I kind of like it better because it's telling us what is the arc where the sine ratio is a half. And so that literally is, here's the arc. And if you remember that little ladybug we were talking about in the beginning, you remember the ladybug? So that ladybug traveled pi over 6 around the circle to land at that ordered pair. So that really is the arc that the ladybug traveled on, was a length of pi over 6 units. So that's kind of nice. You will see in your book both the notations, and they mean the same thing. They're both just inverse. And so why do we use sine to the negative 1? Because it's easier to write. Because literally they said, I can't fit arc cosine right here, but cosine to the negative 1 will fit. So that's what we won. Okay. All right, so let's talk about the y. You don't have to write all these words, but example 1 will work just fine. Example 1, that's a lot of words you don't need to write. What I would like us to do is we're going to graph y equals cosine of x over here on the left side. And then we're going to graph cosine inverse of x on the right side. So we're going to graph the function and the inverse. And it's kind of nice because if you know ordered pairs, then you can draw an inverse pretty easily. So we're going to start by graphing our cosine curve. So this is a good reminder of our graphs. Okay, Our cosine curve normally started at 0 and ended at 2 pi. And it had a maximum of 1 and a minimum of -1. I'm going to cut that 2 pi in half to get pi. Half again, what do we get? Pi over 2 and 3 pi over 2. Very good. And what was the cosine song? High, middle, low, middle, high. All right, so there's our lovely little cosine curve. That's one period of our cosine function. I want to also graph the other half of it over here. So I want to go all the way to -2 pi. So I'm going to go ahead and do a couple more values here. -3 pi over 2, negative pi, -2. And I am going to continue the curve in the same continuation. So middle, low, middle, high. Right there, there it is. All right, so there is our lovely cosine curve. Let's see, the domain of this curve went from -infinity to +infinity, and the range goes from -1 to 1. Okay. And so I don't know if you remember, but we were talking about inverse functions. And I want to know if this graph has an inverse function.
Yeah. So it's right there.
It is the horizontal line test. Very good. So then the question is, in order to have an inverse, a function has to pass the horizontal line test. Do you remember the horizontal line test now? Horizontal line test. Okay, so does this pass the horizontal line test?
No.
No, it does not. It absolutely fails that horizontal line test. 1, 2, 3, 4 little points that it would intersect is a no-no. And so we have to restrict this function so that we can have an inverse. We can't use all of it for the same reason we started out talking about. There's multiple possible answers here, and there's an infinite number of possible answers because I could keep wrapping around revolutions on this circle. And so we want to make sure that there's only just one output instead of a multitude of outputs, okay? And so we have to restrict this so that it does pass the horizontal line test. So let's see, what if I went from 0 to pi? You like 0 to pi? All right, Nick says, therefore it must be so. Nick says we're going to go from 0 to pi. All right, and he's right, which basically is how it worked. A bunch of guys sat in a room and they're like, okay, so what interval should we go from so that we can have an inverse? And they literally said we're going to go from 0 all the way to pi. And so we're essentially restricting the domain of this function so that it goes from 0 to pi. Now, in this small little interval from 0 to pi, does it pass the horizontal line test?
Yes.
Yes. Okay. This is also a better choice than, say, 0 to pi over 2. What's the problem with 0 to pi over 2? It's too small, and it doesn't get all of the range values. So to go from 0 to pi, we get all the values between -1 and 1, all of the possible outputs. So this is an excellent choice. Now, could we have also chosen from pi to 2 pi? Sure, that also passes the horizontal line test in that small little interval. Why didn't we choose that one?
The other one is easier.
Bigger numbers. We're lazy. These are smaller. That's it. So what I'm going to do then is I'm going to label a couple of these points. And so we have this point here, which is 0, 1. Right here, pi over 2, 0. And this point would be pi -1. And I don't know if you remember, but to graph inverses, all we have to do is swap our x's and y's. So I can do that. So I'm going to swap here. I'm going to start with this point. Pi -1. If you make your x and y swap places, what do you get? -1, and pi. So -1 pi is right there. If we take pi over 2, 0, and swap our ordered pair, what do we get? 0 pi over 2. Well, pi divided by 2, there it is. 0 pi over 2. And then 0, 1 trades places and becomes 1, 0, right there. And so what we've, in effect, have done is graphed our cosine inverse curve. And you should know it's not a straight line connecting 3 dots. It does have a little bit of curve, much like this line has a little bit of curve. I'm never going to ask you to graph these things, but know that you can graph it in your calculator. You have a cosine inverse button, so you can graph the cosine inverse function, cosine inverse of x. And I'm just going to go change my window to go from -1 to 1 and 0 to pi, just like this picture is. And then you can see what it looks like. And so what we want to know about this graph is the domain and range. So specifically looking at this inverse function, what's the domain? -1 to 1. And what is the range? 0 to pi. And this is the really, really important part for us. When we're using inverse cosine, our outputs have to be between 0 and pi. And what that means in terms of our unit circle is here's 0, here's pi. We want all of our arc measures, all of our angle measures to come from the top half of our unit circle. And this is where that whole, which one is it? This is important for that. There's multiple answers in here that are going to satisfy our ratio, but only one comes from the top half. Okay, so that's what we need to remember. Domain and range is certainly something I'll ask you about on a test. Do you have to memorize it? No, because we went through this whole thing, right? So you can backtrack that and remember it's just from the regular sine curve. You'll notice that the range and domain traded. And here's our restricted domain as the range now. Okay, so things like that to pay attention to. All right, you good with that? So for cosine inverse, we care about the top half of our unit circle. That's where our answers are going to come from. All right, example 2. Same idea. On one side, we're going to graph y equals the sine of x. And on the other side, sine inverse. So let's graph sine of x. Our normal sine curve went from 0 to 2 pi. I'm going to cut it in half. And again, pi over 2 and 3 pi over 2. What was the sine song?
Middle,
High, middle, low, middle. All right, so there's our lovely little sine curve. And I also want to go in the reverse as well. So I'm going to add in my -2 pi, -pi, -pi over 2, and -3 pi over 2. Please don't go middle, high, middle, low again, because it's a smooth, continuous curve. So I need to go low, middle, high, and back to middle. So we haven't done them backwards like that. So just making sure it's a nice, smooth curve. All right, so here is our sine curve for 2 full periods. And again, let's see, this domain goes from -infinity to +infinity. Range from -1 to 1. But again, what's the problem? It fails the horizontal line test, so it just kills it. And so we have to pick an interval. So what do you think that interval should be? So, okay, so I hear pi over 2 to 3 pi over 2, which is very good. It definitely passes the horizontal line test between pi over 2 and 3 pi over 2. -pi over 2 to pi over 2. Why? Smaller numbers. That's all it boils down to. Pi divided by 2, 3.14 divided by 2 is like 1.5 something. So literally smaller numbers. So that is the interval that a bunch of dudes in a room decided on a few hundred years ago. So that interval is from negative pi over 2 to positive pi over 2, and we're going to restrict it. So that in that small little window, it does pass the horizontal line test, and we can find our inverse function and inverse values. So once again, I'm going to label some ordered pairs here, because if I know some ordered pairs, then I can swap them. We have pi over 2, 1, 0, 0, and then negative pi over 2 and negative 1 as well. And so we're going to go ahead and swap our ordered pairs. Let's start with pi over 2, 1. If I swap that ordered pair, what do I get?
1 pi over 2.
1 and pi over 2. Right there. 0, 0 stays 0, 0. And negative pi over 2, negative 1 becomes? Negative 1, negative pi over 2. And again, it's not a straight line. It does have a wee little curve to it. And this is called concavity. It's concave down and then concave up. Again, that's not necessarily something you need to memorize, because you can, when in doubt, graph it out. And again, I'm just going to change the window to go from negative pi over 2, not pi over 5, pi over 2, to positive pi over 2. And so then you can see there's that little concave down and concave up, which we'll talk about in calculus. All right, what is the domain of the sine inverse function? Negative 1 to 1. And the range? Negative pi over 2 to pi over 2. Very good. And you'll notice these are nice solid dots here. They're actual points. And so again, the range is the important thing that we're thinking about today. Negative pi over 2 is right here. Negative pi over 2. And positive pi over 2, straight up. So we want our angles to be between negative pi over 2 and pi over 2, which I lovingly call the right side. The right half of our unit circle is where we want to pay attention. Anything over here in quadrant 2 and quadrant 3, that's quicksand, land. We can't have any angle measures over here because that's quicksand and we'll all die. So we want small little angles close to 0. And they might be negative angles that get us there nice and quickly, okay? Instead of wrapping all the way around. Okay, questions on that? All right, what part of the unit circle do we look for cosine inverse? Top half. For sine inverse?
Right side.
Right half. Okay. All right. Last. Again. Example 3. We're going to graph y equals the tangent of x.
Oh my god, I've read a tangent.
Don't worry, I'm not going to make you do secant, cosecant, and cotangent.
Wait, why did they just see inverse? Silly set tricks on the
All right. So tangent. Where, ladies and gentlemen, where are the asymptotes for our regular tangent function?
Oh, and 1 is negative. No, wait, don't. I got this. Oh, pi. Wait, it's k? Oh, it's k where x equals an integer. That's domain. I'm just, hang on.
Where are your starting and ending asymptotes? Hi.
Or is it negative pi?
Negative pi over 2 and
Pi over two.
pi over 2.
Okay,
There they are. What can I do for you, sir?
I can come back later, but I have a kid who he doesn't have any geometry credit, so I have to talk to you about an example. I can tell you the whole thing. I didn't want to email the whole thing because I figured it's easier to tell you. He transferred it and they said they gave me credit, but now he's transferred doesn't have the credit. so they want to make sure that he understands it. So I give him, because he's in my math class, so and he's gone through calculus already.
Does he have 4 years of math?
He does.
Then it shouldn't matter.
That's what I said too. But his counselor's telling him that he needs to treat.
That's true. 4 years of math.
Okay. So tell him.
Yep. They don't need it.
All right.
All right. Tangent. Toes to nose. Toes to nose. This was the tangent graph. Toes to nose, low to high, increasing function. And it had the asymptotes at negative pi over 2 and pi over 2. Which is kind of nice because does tangent of x pass the horizontal line test? No. No, there's lots of these, right? Okay. So, but I bet you're gonna know, well, what did they restrict it to? The asymptotes. Yeah, it just works itself out really nicely here. So they said, hey, let's just go, and there's our interval that we're gonna restrict our function to go from negative pi over 2 to pi over 2. You'll notice open circles. What does that mean? Not included. Why aren't we including those? Because they're asymptotes. They can't include them. All right. So the asymptotes here were at negative pi over 2, x equals negative pi over 2, and x equals positive pi over 2. We also had some other values. Pi over 4, the tangent at pi over 4 had a value of 1, which was a nice point. And negative pi over 4 would have a value of negative 1 as well. And so if we were to trade and swap so that we can draw our inverse, what do you think happens with these vertical asymptotes? They become horizontal. That's exactly right, because the inverse of a vertical would be the horizontal. And so it becomes negative pi over 2 as a horizontal asymptote now, y equals negative pi over 2, and y equals positive pi over 2 as the other horizontal asymptote. And we have some order pairs. 0, 0 stays. 1 pi over 4, 1 becomes
1 pi over 4.
1. I know it's hard. 1 pi over 4.
Bless you.
Thank you. And then negative pi over 4, negative 1 becomes negative 1, negative pi over 4. And so we get this. This is the tangent inverse function. And again, you can graph this on your calculators if you want to. What is the domain of the tangent inverse function? Negative infinity to positive infinity. What is the range? Negative pi over 2 to pi over 2. Brackets or parentheses? Ah, very good. Parentheses. Very minor detail, very minor difference between tangent inverse and sine inverse, right? Is that a minor detail that I'm going to test you on?
Yes.
You bet your bottom dollar. That's exactly what I was saying. All right. So, the range outputs for our purposes today, our outputs are going to be between negative pi over 2 and positive pi over 2, which is the right half of our unit circle. Again, so sine inverse and tangent inverse are very similar. God bless you. We care about that right side of the unit circle. What's cosine inverse? Top half. Okay. So, so what do you think if I were to ask you what is the tangent inverse? Never mind. What did I say? Okay, never mind. I was going to throw something off the cuff, and that's just unnecessary. All right. So right side here, last thing we're going to talk about.
Wait, what?
I did not. Okay, here we go.
Oh my God. Which page?
All right, example 4. Find the exact value of each expression. Find the exact value of each expression. So in words, inverse function says what angle has a sine ratio of radical 3 over 2. That's what this statement says. What angle has a sine ratio of radical 3 over 2? So this is the ratio number, which is, that number is from our ordered pairs on our unit circle. And we want to know what is that angle measure in radians. So again, I love circles and dots. And so, first of all, this is sine inverse. Which half of the unit circle am I interested in? The right side. All right, so from negative pi over 2 to positive pi over 2, this is the side that we care about. Now, this sine ratio is positive. Was that going to come from quadrant 1 or quadrant 4? Yeah, because up here sine is positive and quadrant 4 sine is negative. So we're looking in quadrant 1. And since it's radical 3 over 2, I think I've got two options. This low angle and the high one. Do you think it's the lower one or the higher one? The higher one. All right, because this ordered pair is 1/2 radical 3 over 2. There is where sine has the ratio of radical 3 over 2. What angle measure is that right there? Pi over 3 is correct. Pi divided into 3 large pieces. 3 large pieces. All right. So you really got to know your unit circle to make this work, folks. All right. Yeah. This ordered pair is radical 3 over 2 up 1/2 only. It's up a tiny little bit. We have a long radical 3 over 2 instead of the shorty 1/2. So this is not the same. This one matches. Yes, sine is the y value, cosine sine. Remember that. Ordered pair, cosine sine. All right. Cosine inverse of negative 1/2. So again, this is saying what angle has a cosine ratio of negative 1/2. So circles and dots here. So cosine inverse, which half of the unit circle? Top half. So we're looking just on the top half of our unit circle. This is a negative value. Which quadrant is cosine negative? Quadrant 2 on the left side there. And it's 1/2. So again, I've got two options here. The lower option or the higher option? The higher one. The higher one. Why? What's this ordered pair right here? Negative 1/2. Radical 3 over 2. Good. What angle measure is that? 2 pi's over 3. Very good. All right. Remember that cosine is the x coordinate. All right. What angle has a sine value of negative 1? This is sine inverse. Which half of the unit circle are we thinking about? The right half. All right. It's negative. Is that going to be in quadrant 1 or quadrant 4? Good. And so it's negative down below. So it's coming down here. So we need the y coordinate to be negative 1. 0, negative 1. Good. And so what angle measure is that straight down? Okay. So that's a good answer, but wrong.
Oh, negative.
Very good. So this is where inverse functions cause the most trouble. Because 3 pi over 2 does land straight down. That's absolutely correct. But not for an inverse function. We want the quick little angle that gets us there the fastest, which would be negative pi over 2. It's more direct and to the point. That's what we want. instead of this guy, which opened up into no man's land over here in quadrants 2 and 3. Quicksand.